Thank you for the Cisco for inviting me. It's a real pleasure to come to Munich again, especially when the weather is so good. So we really enjoy it. So it's an interesting topic because SQL is, I think, very going on in Hadoop. Quite a bit offerings are there, so I'll talk about some of them or most of them. But I'll give a quick introduction to MapR, people who may or may not know. So Forrester ranked us, this is an American like Gartner. They ranked us as the #1 company, and both in product, they call it the top ranked product. Of course, both Amazon, Elastic MapReduce, and Google Cloud offer MapR as so we get a check from both companies every month because Elastic MapReduce is MapR. And of course, a lot of companies use it. The way to think of MapR is you have one distribution that gives you pure open source. They are like Debian, so totally the main branch. So if you want to deploy Debian, go for it. Another company does kind of like more like Ubuntu. They make it look nice and you can put it on our laptop and it works well. And MapR really is more like a Red Hat kind of model where we harden it and make it good for for deploying in production. So just a quick picture. So we've done a lot of work in the management and a lot of work in the architectural part of it. I'm not going to talk of any of those things right now, but just a big picture. MapR is really giving you all choices. Everything here with MapR is completely open source. The only thing that's we kind of protect a little bit is how we make things reliable. But all the products, all the Apache projects, there are almost like 24 of them now, or 34 of them. Whether it's in their batch thing, whether you do test, Spark, Cascading, Pig, MapReduce 1.0 or 2.0, or GraphX, MLlive, Mahout, even Titan and Graphite we do. In SQL we do Drill, Shark, Impala, and Hive. We have a very big team. And we of course do Cumulo, Solar, HBase as well, Storm, Spark Streaming, and so on. There's a whole boatload of them. And there's more coming out every year because it's a very, very fast changing thing. The point is that we do open source like how Linux does it. So in Linux, it's about providing choice. Whether, like for Linux you get MySQL, Postgres, or SQLite. You get HTTPD, or NGINX, or LiteTPD. So we do the same thing. We give you all the choices, so we can run many versions at the same time, whatever choice of SQL you want. And the other people have some problems with that, so they only provide one version. So anyway, today's talk is really about Apache Drill, so I'll focus on that. So, yeah. Apache Drill is an augmentation for enterprise data warehouse, right? That's the whole reason why this was being done. And why is that? Because you want to do today what's the problem? The things people are trying to do with the enterprise data warehouse is, for example, look at the customer in every which way they come to interact with the company. Today, if I call my cell phone company, the customer service has no idea what I'm doing with the purchasing of the plan actually. And they have no idea what I purchased, what kind of phone I have, anything. Right? If I go to a bank, my mortgage company is different from my credit card company. Even though it's the same company, they don't have the same view. Right.
Excuse me. Hi, is this Hadoop?
Yeah. Oh, excuse me. Maybe we should put this on the outside.
It's nothing on that. Excuse me.
The other problem is regulation, right? We had a bank in spoke to where this was when the AIG insurance company in the United States collapsed. That triggered the whole collapse of the banking system. And this giant bank in New York was asked to provide all the transactions they did with AIG for the last 10 years. Every transaction. So that's like, there's tapes and tapes of material they had to go and find. Most of the tapes they kept in Zurich. and they couldn't find one of the tables. So they had about 90 days to turn over everything, because the prosecution was investigating, and they couldn't find it, and the judge didn't believe they couldn't find it, so fined them $5 billion. Just didn't believe, right? So so the cost is infinite on regulation, and what they would have liked to do is find it immediately and spend 90 days analyzing what's their exposure instead of searching for it. Or probably they found it, but the official story is they didn't find it. Right? And then, of course, try to find out if somebody's gaming the system, right? That's part of the main reason to do this. So what's holding us back? Right? Why can't enterprise data warehouse do this? Well, this is what an enterprise data warehouse looks like. You have all these different databases, which are OLTP, internal, external databases. You throw them together into the data warehouse and say, oh, look, I get all the reports I want. Well, this picture is a nice picture. If I look inside, it looks like this, and then another one that looks like that, and another one that looks like that. And really, they don't really talk to each other, right? Even though they are inside the same system. And consolidating multiple schemas is very hard. Why? Because you're doing schema on write, so the way you read is already determined at the time you wrote it. So you cannot read it in different ways. And essentially that is the main cause of it. So that's the main problem with the enterprise data warehouses. And data shouldn't really be in silos, because you have profile data, business data, all kinds of different data about the person. How do you ask things like, well, what does this guy do in my company? Okay, he's bought this, he's bought that. I think if I talk to some of the giant companies here, they don't really have full view of the person. Or if you're trying to track what somebody's doing, you cannot. You cannot figure out if they're doing something bad unless you can see all the data. And really the data really has relationships that look something like this, which is, it's completely connected in some way, but we don't know which way yet until we go and look for it. So what we really want to do is to keep all the data, but you do it in an economical way. And this is where the Hadoop whole story is. It's fast, it's cheap, and it's flexible. So we at MapR decided to say, let's try to think about SQL for big data, how to think about it. At least we spent some time trying to brainstorm, saying, look, there's Hive, we had a lot of customers using Hive. They're always unhappy about something or the other. Either it's speed, either it's language, or the whole experience. So what we want to preserve about SQL, which we like, is it's very familiar, very used everywhere, very ubiquitous. It's high performance. I mean, interactive speed is very important for you issue a query, it comes back right away, not 20 minutes later. It's one technology. That is, you connect through ODBC, JDBC, you get it. All the tools integrate with it. I don't have to deal with so many variations. And I'm using it as a system of record. MapR solved some of these problems, like a little bit on performance, a little bit on this thing, but the rest are still to be solved, so we did Drill. So we built on Drill. First thing is to allow semi-structured data types and allow schemas to evolve quickly. The other problem is, how many of you are DBAs here? 1, 2, 3. How much do your users like you? I mean, in the sense that, when somebody is doing an application, you're supporting so many groups at the same time as a DBA. And when a developer says, I want this new schema or this 3 more tables added or something, right? You have to measure the performance and see how it is before you allow the person to even do that, right? They want to add 2 more indexes here or something. And they complain this is very slow, but they don't understand what's the impact of doing that, and it's about, and seen as a bottleneck sometimes, the whole process. So we want to allow self-service there. And of course, scale, this is about the big data after all, right? We want to be able to scale. So SQL is here to stay, unlike you see other people saying, oh, SQL is going away because of Hadoop. No, it's here to stay, we know that. But I think the SQL guys also have to admit that Hadoop is here to stay. right? They can't say, but they look at Hadoop as a second-class citizen and say, all right, you guys Hadoop, and you just say big data, but we're the real guys doing SQL. So they have a point, right? So what are they saying? They're saying you can't handle real SQL about Hadoop, right? So let's take an example. What do they mean? So here's a very simple. Of course, you wouldn't write it like this normally, but let's take an example, right? A very simple example. They are right. Apache Hive cannot compute it in any form, whether it is Impala, Hive, Sharp, or Spark, cannot run this query. Right? So if they feel good about it, it's a simple query, they can't do it. Well, the grass is not so green on the SQL side either. The databases cannot do this. You know that normal SQL cannot handle this. You know why? No. Anybody? All the clues are here. Self-described data. HBase has no schema. So there's no type information available for these. Right? So it doesn't know how to run the optimizer, doesn't know how to do anything. So it says it gives up and fails. As a matter of fact, Hive and Impala Sharp also cannot do it. So this is why we did drill. And it's mainly because there's no metadata store definition available. Right? But people are not doing, when you write a JSON file, there's no metadata necessary. It's all in the file itself. So to expect that is changing now, right? So drill was really a lot, invented to bridge the gap between this kind of work and this kind of work, where it's all the schema is actually embedded in the data. Right? There is no metadata server. This gives more flexibility, but it causes problems for structure. So Apache Drill is really designed to work. So let's walk through a quick set of queries in Drill to see what it kind of looks like, now that I put the kind of the groundwork for it. So very simple query. We're reading a file and selecting a couple of fields from it. The big difference is the data sources in the query itself. I don't connect to something. I don't have a TNS names.ora or something that says now connect here, or connect there, or connect there. It's all, I just give it. Right? So the cluster name is there, given, and then there's kind of like a workspace. Actually optional, but it's nice to have a workspace so I can give the query to somebody else and they can run it in their workspace. And this is the path name or a table name or something relative to the workspace. Very simple query. So let me show a little bit. So the types of data Drill can handle is JSON, comma-separated, CSV files, all the Hive types, the ORC, ORC1, ORC2, RK, HBase tables, and embedded types as well. And I'll talk about embedded types. And it can combine them. So here's an example of combining them, where I take a flat file, which has log data in it, combine them with a database of users in my system, look for errors, and then send them an email saying, hey, here's your problem. You have too many errors in your code. And you see a hierarchical structure here as well, which I pulled out of the JSON profile. But we can combine it in any way. So here's another interesting example. So this is the same query before, but this is where it gets really powerful. I can do a same query on the entire data collection by just providing the directory name here. So I truncated the path. I can truncate anywhere I want. But now if I organize my logs by year and by month and by week or something, now I can query all of them at once. I can even use so what Drill will do is give you variables that you can refer to in your query that are the directory components here. So I can say, give me the errors for where directory 0 is greater than 2012. So I get all and let's say group by month, right? Group by directory 1. So it comes out as directory 0, directory 1, directory 2, directory 3, and so on. And you can have synonyms for that. So you can have year as directory 0 and month as directory 1 and so on in the query, using the as thing as a synonym. And you can say group by month, where year is greater than 2012. Let's say. So I can put them inside the query, just the path name. So it's very, very powerful. I can now have a whole tree of stuff, organized any way I want, and just a simple query can get the whole thing. Give another example. So let's walk through a JSON example. I have a database of donuts, and it has the name and the fillings. And the fillings is kind of interesting. Look at this structure, right? This is usually not possible in regular databases, where I have repeated fields like this. This is an array or a list in JSON, and this is a map in JSON, a list of maps. So how do you query this? In Java, you say run SQL query, and then you get a cursor. While our next, you read the name, classic or chocolate or Boston cream, and then read the fillings. But that's a list. So you get another cursor. You can walk through the cursor and read the calories. And if the calories is greater than 400, you say this donut is bad for you. Right? Don't eat it while you die. Well, this is easy to do inside a Java program. Now, the equivalent, can you do it directly in SQL without doing this? Can I just directly do it here? Right. So, same thing. We flatten the maps in JSON and other nested records. So a way to promote the internal field into as a first level field by using the flatten we added. So what it does is it takes the fillings and promotes it as a first class record. And then I can directly use it. And of course, now we're looking for donuts that are good on a diet. This prints nothing. So it shouldn't be donuts on a diet. Right. Another way is there's a Fluent or, so you can actually do this directly. Right. Another way we can do this also in Drill, a second API that we support is a Fluent kind of API. So now we can also do, instead of doing this, we can also do something like this, where donuts.json, less than fillings.calorie, 300, get all of them. This is more like the Mongo style of writing or the Fluent DB kind of style of writing. And the rest is the same. Okay, here's another new example on how to deal with JSON, but this is a different example. So what we have now here is that we have a HBase table, and the table is called donuts. And inside the HBase table is a column family CF1 with a field, the column CF donut-JSON. HBase doesn't know about JSON inside it. HBase is typeless. Right? So what we're trying to do now is we take the convert from structure, just like we did with like convert from string or convert from let's say date or UTF-8 or something like that. Parse it. So we can put a parser here. You can put different kinds of parsers. Use a JSON parser, you can use XML parser, you can define your own type of parser for the data. So we take the embedded thing, promote it, and then use it directly. Very interesting kind of thing. So now we are looking at data embedded inside another structure.
You can also use HTML, this would also be interesting.
Yeah, I don't see why not, because that's an API we put in Drill, you can plug in whatever you want. In fact, if you're in, sorry, somebody answered the question. Yeah, HTML question was, can you put in HTML as a parser? Yes. You can also put in any other parser. For example, we were talking to a semiconductor company, and when they do yield analysis on the process of building the wafer or chip, they want to be able to parse that file directly without having to sit down and do an ETL process and write some customized code for us to translate it. It's very, very powerful being able to do this. So I can grab the data, parse it instantly, and use it. Of course, it's slow. It's not as fast as native types, right? So maybe you want to do it once and then afterwards start using that side. but it's very powerful. Let me give you another example. I can now queries inside the JSON records. So every JSON record itself can be a whole database. So let me explain what I mean. This record itself can be arbitrarily long, and I might want to query inside that record because I have thousands of fields inside a single record, and I need to look inside, and I want to write some queries there. Right? So for example, let's say I want to say, get all the donuts where at least one filling is greater than 300 calories. So I actually need to iterate on the fillings array, which can be, I might have 5,000 entries there. So how do you do that? So again, the same previous query we had, we just put it there. But now we introduce a new thing, which we got this from Dremel, is to do within record. So I'm doing that within record as min-cal, and then look at those. Again, very powerful. I can do the opposite coming out soon, is I can actually insert into people, this kind of stuff. Now it starts looking like almost like Mongo. You can give it an ID and put things like that. Except a lot more powerful. It's running on a whole cluster, the cluster is reliable, you're actually getting real SQL. So what are the challenges? One of the main challenges is the schema can change over the time of the query. Right? Now how do you deal with it? Okay. Because while it's easy to show all this, but I've shown you regular examples. What if I show you regular examples where fillings was this array while you're running the query, and now it becomes a scalar. It becomes like a date or an integer. Right? So what we have to do really is to be able to reconfigure. So I'll talk about how drill works internally right after this. But what you have to do, what we have to do is to detect that and reconfigure it. Because I'll talk about this in a little bit. And then we have to support more advanced optimization based on actually the data which you're parsing. This is not such a bad thing to do, by the way. So if you look at, let me give an example where this becomes useful. So let's say you have a log. You're doing a printf in your code to produce the log. Say printf, user, whatever the error message with, and he did it on this IP address, and this was the reason. And now somebody comes and says, hey, error message is insufficient. It's been running for a few months like that. And they say, no, it's not good enough. I now want also the host name and the port number, and I also want the process ID. Because you forgot to print those, I can't find out which one it is. All you gave me was the IP address. Okay, let's do that. And by the way, you're printing the wrong IP address. You're always printing 127.0.0.1 or something. It's very useless. So then he writes the new printf statement. Now suddenly your log files have a schema going one way before, and suddenly after that it's a completely different schema after that. So that's actually good. The schema changed. But I can still do the optimization because you want to go fast on this part and you want to go fast on this part as well. Right? So it's natural to have that change in programs. And here's another example where we are actually combining Hive, which has metadata, against something that has no metadata, and you can actually combine the two. So the point is, what we have done is very interesting here, if you look at the big picture here. So the source is directly specified. I can just take any two directories or any 5 files and just join them. So I don't have a concept of a database anymore. Right? The concept of a database is in your mind now. You can make a directory and put related tables and files together. That's a database. So you can have a database, I can have a database, you can have a database. But if I want to run a query pulling two data from those two, I can do it. I do not have to talk to anybody to say, please ETL from this database to this database and do the query. It's extremely powerful. I don't have to contact a DBA to do that. I don't have to go and get ETL tool to do it. I can just run the query, and if I like it, I keep the results. I just need to file permissions to look at it. or database permissions. So let's go and read the covers on what's going on. So the first architecture picture, I think you've seen this before maybe, is we have a drill bit running on every node, and they all register to Zookeeper, and that's how everybody finds them. So when a query comes to any drill bit, can come through JDBC, ODBC, protobuf, anything. And any drill bit can do this. It executes the plan, and it distributes the work, and the results can come back. And the first guy that was contacted does the aggregation, and then goes on. Right? So what are the stages of query planning? You issue a query, it goes to a parser. The parser then takes the human readable thing and converts it to a logical plan, which is the machine readable thing. And then the logical planner runs and produces a physical plan based on heuristic and cost-based. And then the physical planner runs and produces a query like a distributed execution plan kind of thing. And then the plan fragments are sent to the different drill bits and they execute and come back. This is the basic stages. Internally it looks like this. Inside one drill bit, we have the query parser, an optimizer for going from the logical plan to the physical plan, and then a scheduler, a foreman, and the operators that get pushed out, and then an interface to the storage engine, depending on what the capability of the storage engine is. If drill has to do the work for the storage engine, or the storage engine itself can do it. So we can push down operators into the storage engine based on the capability. Right? And we have entry points everywhere through RPCs. So you can enter from here, you can plug in to replace different parts. The data parser I talked about, convert from, is actually over here. Right? So the parsing of the embedded taxes inside there. So a query that comes in, maybe comes in through JDBC, optimizes, goes to the scheduler, it schedules it, goes to the foreman that drives it to all the places, and then goes to all the nodes. So I'll talk about these things. So how we do columnization and vectorization. Drill is basically a vectorized execution engine. Meaning even inside the code, it's always dealing with vectored data. Instead of, if you look at Impala or Hive or any of the other Spark or any of them, Shark I mean, even though the data on the disk is laid out in a column fashion, internally it's still it's row based. Versus in drill, it's actually really even inside the entire code is vector based. Which means we hold a column, so anyway I'll talk about that and tell you about how we do the optimization and the pipelining. A little bit about runtime compilation, what needs to compile, how we figure out how to compile different things. And late binding, which is what we have to do for discovering the schema changes. And then we do how the pipelining has to go with the late binding, because in the middle of the query the schema has changed. So while the results are coming back, suddenly we say, oh, put a break here and rebuild and recompile. And everything is extensible, so we can do that. So quickly, what's columnar representation? If I have a database that looks like this, you basically go down each column and produce a piece over there. Right? Take that and save it like that on disk. Then you take the next column and go down that and save that on disk. And then you do it for C and for D and for E, so on. Right? So the database is actually laid out like this, like this, like this. Right? Versus rows wise. Why is that good? In some, OLTP doesn't do it this way, OLAP does it. Why is that good? Well, the values in the column then are stored next to one another on disk. And so if the types are similar, the compression becomes much better. And if you have a table full of URLs, and let's say page rank and so on, most of the prefixes of the URLs are going to be the same one after the other. So if you store them by the column, the compression is going to be, I have a bunch of text followed by a bunch of numbers, followed by a bunch of, let's say levels or something. And they all will compress nicely because similar data is nearby each other versus this. Better compression. Now here's something very nicely I can do is I can save them in ranges and do a range map. A range map is basically saying that in that range, what's the minimum and maximum of that column at the top, I can say, save in a header. So when you're doing scans, and you have a greater than or less than kind of operations in the scan operator, we can skip that entire, even reading this, because the range map says I don't have to look at it. Okay. So we can only retrieve the column. And then, of course, the most important thing is we're never looking at all the rows. We're usually looking at the subset of the rows in the query. Sorry, subset of the columns. And we're not looking at all the columns. So then we have to only read the column we care about. Maybe that's A, B, and E, and we can skip reading this completely. Right. And very interestingly, we have some very cool optimizations here where we can do aggregation. Depending on if we understand the compression scheme, then it's not gzip or LZ0, LZ4 or LZF or something like that, or whatever the other different LZs are. It's if we understand the compression technique used, we can do aggregation without decompressing. I'll give you some examples. Right? So for example, let's say we're doing runtime encoding for numbers, where we know the numbers are going to be similar. So we're saving the value in the run length. So we have 2 is appearing 4 times, and then 8 is appearing 10 times. Okay. And if you sum all the records, if you do the normal way, you'll decompress to create that, and you'll add them to do that. If I know that that's what I'm doing, I can just do a simple arithmetic like this without having to actually touch the data too much. It's very, very easy to do this. I'll give you another example, which is a little bit more complex. Let's say I'm encoding now in a data dictionary, where I have Rupert, Bill, and Larry, whose bit positions are 0, 1, and 2. And so now in the data, I encode how, so this is Bill, Rupert, Bill, Larry, Rupert, sorry, Bill and Rupert. Right? That's how, and I have to sort this. Right? If normally, if I do that, I have to decompress and then sort. Optimized way, I can first sort the dictionary and then sort the bit pack values, because I'm sorting by name first, not by bit position. So I sort the names, right? And then I sort the bit pack values, and I only have to do 24 comparisons of the fixed with dictionary bits instead of decompressing the variable string with string lengths. It's way cheaper to do this. All right, here's another interesting one. Now we have to support repeated field, which the Schrodinger's catches. You don't know if it's dead or alive. Here we do both in both states. So typically in SQL you do true, false, and unknown. And we had to add one more to say this is actually an array, say repeated values. So we added that. And so now we store batches of values like this. Now I'll talk about how it's vectorized internally, where we have a list of values with the same schema and with the 4 value semantics for each. Right. And it's shipped around in batches. So all the work is done in drill as columns of maximum 256K. So when a drill process works, it says, okay, fetch 256K from disk. And while you're working on it, get the next 256K. This work is finished, send it to the next machine or the next node, and I'm going to send this out and so on. So whenever we have a problem with the schema, we interrupt always at this 256K boundary. You can stop the work and then rerun the query based on that. And so it's very interesting what we have to do for the RPC. Because we do one request, we're going to get back a batch of these things one after the other. Right? So the RPC design had to be different. So I do a query, and typical RPC is request reply. But here is a request, and I'll keep getting replies until it tells me it's done. And by the way, while the reply is happening, the schema can change, because it told me that now the schema has changed. Right? So we had to do this. Otherwise, you have to rerun the whole query again, and you lose, right? Because there's no way to change the schema in the middle.
I have a question. What is the block size of your HDFS in MapR?
MapR it doesn't matter. This is Apache. So.
So because typically
it just block size is 128 meg or 56 meg. So block size is, question was what is your block size? Your block size is in the 100, 200 megabytes, right? 128 meg or 256 meg. But we're doing 256k bytes, so it's a lot of batches. But we have to detect schema change quickly, but so the trade-off is this, right? If the batch is very big, we do have lost a lot of wasted work. If the batch is too small, then we cannot optimize for quick operations like the optimizations I showed or reading the disk. So we kind of pick this number as an intermediate number. We can make it bigger, smaller. Also, when you do RPC, if you make it bigger than this, the RPC, the network gets into trouble. Most switches, they don't like big RPCs, they like smaller, more like, if the Ethernet packets, this is how many Ethernet packets, this is 250 Ethernet packets or something. So single RPC, if you restart that, repeat that, it's quite a bit. You have a concern?
The question is only because if you touch several blocks with your query, then this is my concern. This was the question here.
Yeah, it will be several blocks. I mean, we'll read the same. So the data is actually laid out in this fashion, right? Let me go back to the earlier one. It's laid out like this. So this will be maybe 100 meg or 200 meg, but it's not actually, it will be 256k is this much. And then the whole thing is repeated, or a megabyte or so is this much. So per K does a megabyte, and before repeating. So I have A, B, C, D, E, then again A, B, C, D, E, then A, B, C, D, E, and so on. So we did 256k as the batches. But also we have to look at the key sizes. So we also make sure we don't send too many keys in one shot because they have to redo this. So some simple, I'll run through very quickly. This is how we represent a byte buffer, fixed value vector. And the way it works is that we have a byte buffer holding it, and then we have a vector of bits. For example, if you have nulls, we just put a 0 there to tell you the pointers there. So when we sort things, we only sort another vector here without actually moving the values and so on. So it's all sorting the pointers rather than sorting the actual values. So we don't move the data inside the code anywhere. Right? Even repeated values, we kind of keep it this way so that we can sort only the pointers. So sort of moving the actual data. So we read from disk, we never move it around, we just sort internally on a separate vector on the side. I'll just run through this quickly. Again, we read it through a byte buffer and then just represent strings like this. This is how we do repeated fields, where we can keep an offset and count. I can give you the slides, it's not a big deal, you don't have to really go through it. But basically, we really operate on more than one record at a time. We're not looking at, it's not row oriented, it's really vertically oriented. And we try to demote or promote to word side manipulations as far as possible, so that we can use native. So when we run, we compile it natively. And we try to do pipeline kind of thing, like simply instructions. Right. And sometimes we actually manually code the algorithms when these guys can't handle it. And then we also do logical vectorization when we use bitmaps. So one of the things in queries that happens is, if any of the part is a null, we can kill the whole query right away without actually having to run it. When you have the semi-structured kind of data with missing fields and sparse structures, so you probably have a lot of rows of nulls for certain columns. So it's very important to handle null checks very quickly. I mean, so we do that very, very, very fast so that and we avoid the branching to the null checks. So we just put nulls in. You can immediately compute on the bit vector itself if you have any nulls and kill the query right away. So here's another thing. Why do we compile expressions? Well, if trivial and simple expressions, the performance of compilation versus interpreted, kind of gets very advantageous when you start going to compile expressions. Right? So we use this thing called Genino. Right? So JIT is smart, but you really have to actually compile the whole class instead of doing JIT kind of compilation. So we use something called Genino, which is a Java-based Java compiler. So it's not just, sorry? Question? You know you've used it?
No.
You've heard of it? No? So you know what I'm talking about here now? Okay, so when you run in Drill, Drill will generate the query and actually generate Java code. That has to be now compiled and run. Okay. JIT is just one level of compilation. If it's compiled, fine, it will go into JIT compilation, but that's not as good. That's running like this. Versus if you do Genino kind of compilation, we recompile the actual class down, it gets even faster. Right? So let me talk about what the Drill compiler does. So we use code model to generate the code. So we go from logical plan, physical plans, and now physical plan generation. We generate the code and compiles the runtime bytecode. But we might have pre-compiled bytecode templates because we hand-coded some algorithms, because that's actually better than what this can generate. Right? We don't know which might be better. So we merge the bytecode of both the classes, and then produce the class that's actually finally loaded into when you run it. Okay. JIT will operate on this. Okay. JIT won't operate out here. Right. So
just one question.
Yeah.
How do you identify a situation when it's better to use one of the pre-compiled ones? Is that done automatically?
No, I think we have some templates we know which is better. Especially where the decompression stuff is concerned, where we know how we have packed it, and we know what the query is. Let's say average, some range checks, things like that, which you do aggregation kind of type of queries. Better to do this, than to do this.
So it's checked based on the query, not on
Not
the
on
code
queries
generated.
We need some. I think this needs some improvement. I mean, but it's a pretty good idea to do it like this. It's a very sophisticated technique, and I think if you guys are into compilers and all that, you need some help. So if you want to contribute something, so it's pretty. We have some of the guys who work on GCC helping us with this. So let me talk about optimistic versus Drill is considered optimistic. Optimistic means if something fails in the thing, we restart it. So let me tell you what it means. And this you already know, but I'm just going to say. So if the speed of the execution is very fast, like I do LS, I don't checkpoint LS. If LS fails, I just rerun LS. Right? I don't try to make it recoverable or anything like that. I just say, even if I have a pipeline of commands, LS, pipe through sort, pipe through grab, and it fails, restart it. I don't care. It takes so quick to execute, why bother with all that, right? But once I start getting more complex work, the speed is still pretty high, but the work is more complex, I start checkpointing. Right? And large DB data warehouse, even if I do compile, or if I compile some code, I checkpoint using .o files and .lit, .out. To create the .out, I might create some shared libraries and so on. Hadoop, of course, is extremely checkpointing. This is expecting whole machines to blow up continuously. Like, Drill kind of is sitting, so there's really no need to checkpoint here. We checkpoint all the time. Drill is kind of sitting in this range. The expectation is to run as fast as LS or command pipeline. So we can save a lot by not doing any checkpointing at all. But Drill will still page to disk if the joins are very big. So the paging to disk is still, has to be in a way it doesn't get corrupted. But that's really not checkpointing, that's just paging to disk. So recovery code is really trivial. All we have to do is inside a drill bit is discard all the queries. We're doing it batch level, and one of them you know, the 256K patches, if any one of them fails, you just blow the whole thing and say rerun the query. You're not trying to recover. And it actually allows us to do this. Because we don't do checkpointing, I don't have these, what we call barriers, where I say I have to checkpoint before I can run the next step. So we can actually do results as soon as the batch, start sending results as soon as the batch is large enough. So for certain queries, in fact, Drill will start giving you results even before the query is finished execution. Right, so you can start seeing the queries, the results start coming back. On places where you can do it, of course, when you have barrier in the query naturally, then you won't get it. Right. Aggregations really move forward to this kind of stuff. But if you do, let's say, limit aggregations, then you can start doing this as well. So pipelining, I talked about this already. Record batch is a pipeline. It's the unit of work for Drill. And the operators work on a batch. And the raw operator reconfiguration happens at batch boundaries, right? So this is some animation I put in. I should not have done this. Okay, it's there. It's very. Any question? Somebody is.
Does it all work in parallel with Hadoop NTR, or is it integrated?
So the question is, does it work in parallel with Hadoop or is it integrated? Yeah. It's a standalone. Apache Drill is a standalone program. You can run it. It uses Zookeeper to find things. It uses the HDFS API to run. So we are testing both on Apache and on MapR at the same time. The work is being done on both. But it's open source, so anybody can take it, run it. It'll run on anything. In fact, we've also made it run without Hadoop. So you can just take it and run it on your laptop. No Hadoop necessary. But it's completely standalone. So again, the pipelining actually happens over here at this level, not anywhere over here. So it also lets you do random access, where you can do sort with when you can sort with the copy or registry. I think I talked about this. And it avoids serialization, deserialization, because since we only work with the vectors as a side with pointers to the data, we never actually deserialize the data from disk unless we have to actually look at the field. But we don't have to re-serialize again to send it. We just send the vector that says, okay, these fields are really now no longer existent, and send the whole thing over. So it makes CPU much less useful. We've done a lot of effort, although Drill is written in Java, right, we try to avoid the Java headaches. So right from day one, this is the fashion today. So from day one, we adopted the fashion, which is to go off heap and do the memory management completely in C for Drill. And we got some advantages. Because we went off heap and because we had a complete format for even for the intermediate results. Because how we store and work in these batches and intermediate results, we have a full specification and it's batch based. And it is off heap, which means I can actually now think about putting operators directly in C. And now I can do very, very fast things, like fast Fourier transforms, completely in C without trying to do it in Java. So it's a big advantage of some of the things we can optimize and put in there. I think we've done a few things like this already. I don't remember which. And the best thing actually says is one of these things is actually if my off-heap memory gets overflows, right? Even if the off-heap memory now starts overflowing, I can write to disk in the same batch of 256K overflow to disk to do really large joins. It's completely automatic and dynamic. Including because the full specification is there already. And in fact, in the future what we're doing is, can we also write this to, can we write the intermediate results to disk also? To hold on to, because if people rerun the query with a slight modification, we can just use the intermediate result immediately instead of trying to go and touch the data again. Right, so Drill also has the advantage that the caching is external to the database itself. It's not part of the, we don't require HPs to build this for us to be able to do caching at the Drill level, or we don't require Hive to do it, or the ORC format to do it. We can do it independently. independent of the data because the cache is kind of part of the system. It's the same system used. So now, how are we doing in time? Everybody's brain is fried, or it's a pretty intense topic, right? So
One question.
yeah.
We were talking about this package size that you are sending around between the drill bits.
Yeah.
So did I get it right that this does not contain the real data, but just your vectors with the pointer?
No, it contains both. It contains both. It contains the real data and the vector. But the real data is never unpacked and then repacked. Because we send the whole data as is we read from disk, but we include the vector as the header. So the receiving side knows to only unpack the things it needs to run the query. I mean, as it is, it's smaller anyway because we're not sending the whole column.
I'm just asking myself, why are you sending around the data if it is accessible from all drill bits anyways?
Then I have to read the data again, right?
Right.
From disk.
Right. You said unpacking versus reading from disk plus unpacking. I'm not sure. Just because of the concerns
So the vector representation. So the vector representation will have to be different, then, right?
Okay.
The vector representation will have to say file name and offset for a file. But then if it's HBase or some other more complex structure like
you are turning the metrics. And
yeah, it's going to be very complex to remember how I got it to begin with.
Sure.
Or if I did, like, say, a JSON where I did a flatten, I think it's going to be very difficult to figure out.
Okay.
How to only send portions of other records. It's going to be very tricky. So I think sometimes simple is probably maybe better. But that's not a bad idea. Maybe that optimization we can do for files. For flat files, like just simple text files, I think that works. Parquet,
but then if you don't put the data to this, and you have the problem with consistency, because meanwhile the data is changed and the vector points to the wrong data. So technically, it's very complex to have a consistency.
That's a very good point.
So for log files, I don't have the problem. So.
Yeah, but if
you're appending, you don't have the problems. But any real database, you have a problem. Yeah, I have to send all the keys then. Yeah, it's a good. Yeah, that's actually the most important point. If I have a real, like a HBase or something underneath, and I'm inserting in the middle, then I cannot send anything useful. It's better sending the data itself.
H5 is never inserted in the middle.
H5 is
always appended.
Logically. Right?
Yes. Yes, it was physical, it was only appended.
No.
Logical, you can insert.
So logically it's inserted in the middle. Physically it's of course appended,
yes.
because that's HDFS. But it is, drill doesn't know the physical representation. It's not looking at the physical H files. It's looking at, it's going through HBase, through the region server. Right? Okay, optimization. So Optic, we use Optic, which has been around now for I think 8 years or so. It's this guy who's been working on optimization in the Java side. Anyway, Optic was a single machine optimizer for like a MySQL or Postgres optimizer. And so we had to, there's a pluggable way to first add rules and costs to it. So we had to add the rules for distributed plan generation into Optic. We did that. So if people are, there's a lot of research done on this, by the way. There's tons of research in this area. Actually, Microsoft has done very interesting work here, very advanced work. But, so we had to add this cost of moving the data into the physical plan. And we had to enhance Optic to, once we did this, we get several plans for the same single plan on the top. So we had to enhance it to explore parallel query plans at the same time. Right? And then we had to add network cost, which wasn't there, and kind of the data locality cost to it. And then we also added the cost of the storage engine features to say that which one is better to push down operators. So these things didn't really exist in the Optic framework we used, but we extended it completely. So I think now Stinger test guys and the Impala guys and the Sharp guys are looking at the work we've done here to put it into their stuff. Just from there. The other one, so now we have to look at also other things like a distribution property of the operators, right? So are doing a hash or a broadcast or this thing, and so now we can do what kind of exchanges happen, right? So we do two-level aggregation, which is we do an aggregation at the local node first, and then we do a aggregation at the higher level next, right? And then we enumerate everything to figure out which one to use, and just use the cost to pick the best. So we have to enhance, like for example, HBase doesn't know how many rows it has in a table, right? So we even just to do simple thing like a join into HBase tables is problematic because which one should be the inner one, right? It doesn't have a count of rows and things like that. So we're enhancing HBase and things to at least keep an approximate count of what's going on. Right? RK has a count, other things have a count, so we need to look at that. So, and we do aggregation, we might do more phases, but right now we're doing only two. I think, okay, I'm not going to go in more detail, I was saying what is this. But I think you've heard of these terms before, right? So at least you can do partitioning versus broadcast versus sorted joins and so on. So anyway, I'm going to summarize because I think it's, so we want to do flexible, analyze certain subscriber central metadata, doesn't matter which way it's stored, and nested data, and reuse the investments that you have already in all the tools that we are as well as high. So what Drill really was designed to was to have frictionless analytics with plug and play on everything that's already there. So it's kind of no investment is, and we produce the files also in whatever format you want. So that you don't like Drill, you can go back to using whatever you like. So it's really, really, yeah.
Can I reuse my high PDFs?
Yes, 100% compatible. So I put the roadmap up, I should have put the other one first. That's what I wanted to put up. Those two slides got reversed. I'll show the roadmap next. So this is kind of giving you a comparison of all the different things. I can give you this. I think somebody will post it up, I'll give the slides. But basically, you asked about Hive compatibility. So we have Drill, Hive, Impala, and Shark. Shark is Hive on Spark. The disk format compatibility is everything that the guys do, plus the ones that don't have strong schema, like regular text and JSON. We haven't done the other parsers, but the plugin framework is there, so if people want to put parsers for HTML or other things, please feel free to do it, or your favorite format that you use in, let's say, parsing X-ray images, or parsing genome files, or genome sequencing files, or parsing semiconductor yield analysis files. HBase M7 is that we can push down and take advantage, because we have a pluggable way of querying the database to see what capabilities it has, and compensating if it doesn't. Right? So that's some of the issues there. Fully, Hive or schemaless. SQL is actually ANSI SQL. Full SQL plus more. Hive compatibility, I thought you asked, was the problem is the Hive subset. Impala, you cannot do all the Hive UDFs in Impala. They're adding as they go along. The others are all full compatible. Impala isn't. Large data sets, in these guys, you run out of memory, you're in trouble. And nested data is there. And some measurable concurrency. We claim it's high, but we'll see. Now I'll give you the roadmap. So this is coming out now in June or end of June. It's very close to getting a beta out of this one. I think the GA might be some more time, but we won't give it to everybody to use. I think some people are already using it. I know Christian demonstrated on JSON at a customer, it just worked. I think you were using it, Henrik was using it.
I'm planning to.
Planning to, okay. Yeah, you can try it out. It's fairly easy. Like I said, you don't even need to run Hadoop to try it. So truly, it's not MapR, it's really open source. But we are going to do H-based query speed up because I think getting rows and columns are much better to deal with than flat files. So, and adding nested data functions so you can do JSON. And so let me go back to this slide once real quickly. So performance. There is no performance mentioned here, right? You know why?
Hard to compare. Anyway,
So how do databases compare performance to each other?
there's strange benchmarks.
Yeah, so exactly. So the benchmarks of people, if it's OLTP, you have TPCC. If it's OLAP, you have either TPCH or TPCDS. And I think still TPCH, TPCDS people still argue about. So what these two benchmarks do is there's a set of queries you have to run on a database, right? And so it gives you two numbers. It gives you how many queries you could run, how many number of concurrent queries you could run, and then the cost of doing that, which is the dollar per operation, or dollar per query, dollar per operation. Right? So those are the two things. So they can't run all the queries. That's the first problem. Right? TPCH queries are not possible with any of these. So drill is going to do everything to go fully SQL. So I think it's already running all the TPCH queries.
There is an adaptation for Hive, as I know. TPCH, there is a project where
They're trying to do that, right?
they
Now I go to TPCDS, it gets more complex, and then suddenly you have a more commercial. Right? So yeah, actually that's the point of this slide too. Right? The point of this slide is that with MapR, like I said, we are unbiased. Right? So we don't know, all these guys are new. Today one is good, tomorrow another one is good, day after tomorrow the third one is good. Again, first one is good again. And we give you everything. So, and we make sure that the file formats are all supported. So as long as that's going on, you can replace, if you don't like it a certain, if you don't like something, you can replace it with something else. And then we're going to operational SQL with drill to make it ultra fast, so that we can do single line, ultra low latency queries, like almost a single row update, insert delete kind of things. And start doing the workload management. We try to figure out the query and complexity and see, since we're doing in batches already, we don't do all the work at once. We're already designed to do workload management from the ground up. Everything is already designed for that. So now we have to do the way to measure which query is taking how much time, and maybe do some queuing inside that to see if you have 25 queries running simultaneously. Maybe you do workload management between the queries and everything. So if somebody wants to help us build this, it's a very interesting project.
Time frame?
Once we get this thing done. Yeah, but if you want to do that earlier, you can do that. Not a problem. So, Jacques, he runs the drill project. You can talk to him. So coming back, like I said, we're really about unbiased choice here. We give you everything you need as a MapR. We have 20 people working on drill at MapR. Very big team. So not just drill, they're working at Hive, drill, and Impala. So they look at the whole picture. And they're really some of the top people in the database technology people. We have ParXL, Teradata, Vertica, DB2 people. Some of the guys who really built the core engines are working at MapR. And we have fixed some of the toughest problems in Apache Hive as well. We did an enormous amount of contribution to fix some of the things. So these are the people who kind of joined in to help us build this. Microsoft, LinkedIn, Oracle, Facebook, Visa, even Concur. And we had a couple of hackathons this year already, where we kind of took different portions and just built it up. Like for example, the compiler merging integration was done in a hackathon. So So getting started, like I said, is very easy. Just download and start running local files. Do a bunch of mailing lists you can join. You can open a Jira if you don't like something. Or you like some new feature, say needed. This is the information. Thank you very much.